and he's going to tell us about the habitable zone from a population-based perspective.
Hi everyone. So the coffee break is coming, so please hold on. So we saw a few images of the habitable zone during this talk, and it was visualized as a stripe around the stars. And I will talk about a different way to consider the habitable zone. So a planet is in the habitable zone if it has liquid water on its surface. So this is primarily a condition on the surface temperature and surface pressure. And here you see the phase diagram of water. Temperature is on the x-axis, pressure is on the y-axis. Water is in solid form in the blue regions, liquid form in the green regions, and in vapor form in these gray areas here. So where do some of the solar system planets fall on this figure? So Earth, we have roughly 290K surface temperature and 1 bar surface pressure. So we are safely in the green region, which is great. We are indeed habitable. For Mars, the surface of Mars is somewhat cooler, and the surface pressure is only 600 Pascal, which is below the triple point of water. And therefore, water can only be in solid or vapor form on the surface of Mars, so Mars is not habitable. The other extreme is Venus. Venus has a 1700K surface temperature and 70 bars of surface pressure, so water can only be in vapor form on the surface of Venus. So what influences the surface climate? This is really what we want to find out. And this is the stellar properties, the luminosity and the effective temperature of the star, and that kind of things. The orbital parameters of the planet, which determines how much stellar flux arrives to the planet. And of course the planet properties, the atmosphere, surface, and the interior. So what we know from observations is the stellar properties. We also have a good handle on the orbital parameters, but most of the planet properties are observationally unconstrained. We have no clue about the atmospheres of the small planets, surfaces, and the interiors. The interior is in yellow because from transit observations, we know the planet radius. From radial velocity, we know planet mass. If you have the average density, you can start guessing the interior properties of the exoplanets. So the question I really want to answer is, what can we tell about the surface climate if we know so little about the planet properties? And the way I do that is the following. I want to describe the habitable zone as a probability function. What is the probability that an exoplanet has liquid water on its surface, given the stellar type, the planet radius, and the incoming stellar flux? And I use here the planet radius because I'm interested in transiting planets. If you want to work on radial planets, you can use this planet mass in here. And so once I have this PHC function, then I want to estimate what is the occurrence rate of habitable zone planets. The main concept, how I do this, is to treat the stellar and planet properties as random variables. And if you do that, you can assign probability density functions to each of the random variables. And as I said, some of them are observationally constrained, and for those I just sample from the observed distributions. But there are a large number of random variables that are observationally unconstrained. For example, the surface pressure, the atmospheric composition, and the surface albedo, these kind of things. And so for those variables, I generate synthetic PDFs based on what we know about solar system planets and moons, and what we expect to find for exoplanets. And so I sample each variable, and then I use a 1D climate model to calculate the surface climate of the synthetic exoplanets. And I repeat this several times, and in this way I build up synthetic exoplanet populations. And the final step is to study the subpopulation that can have liquid water on the surface. With that, I can constrain PHC, I can have a handle on its uncertainty, and I can also calculate what is the occurrence rate of habitable zone planets. So here's a result. So this shows the average probability that an exoplanet has liquid water on its surface for M-dwarf stars, that's the stellar type. On the x-axis, you see the incoming stellar flux in units of solar constants. So this is where the host star is, and these planets are close to the star, these are far away. And the y-axis is the planet radius in units of Earth's radius. So in each of these grid cells, there are millions of synthetic exoplanet scenarios. And what I do here is essentially count what fraction of those could have liquid water on the surface. So there are a few things that you can already see here. If a planet is larger than roughly 2.5 Earth radii up there, there is not a single scenario where this exoplanet would be habitable. That's because these planets are too large and they probably don't have a solid surface to stand on. Other thing is, if an exoplanet receives roughly 2 to 3 times more stellar flux than Earth does, then these exoplanets have too high of a surface temperature. So again, they cannot be habitable because they are too warm. And so you have this intermediate region here where some fraction of the exoplanets could have liquid water on their surfaces. So this is the average of average pH value, but at each given point, I can also tell what is the uncertainty. So let's take a completely arbitrary example. Let's assume we discover an Earth-sized planet that receives 1 solar constant stellar flux around an M core. So the average probability that this planet has liquid water is 40%, but the uncertainty, the range, could be anywhere between 0 and 70%. So we have very weak constraints on the habitability of this exoplanet. And that's because we know so little about the atmospheric properties of these exoplanets. So I said I also want to calculate the occurrence rate of habitable planets. And to do that, I use a data set of Lessing and Charbonneau. That's about small planets around small stars, M dwarfs. And so what I find is that the occurrence rate would be anywhere between 0.001 and 0.3 planets per star. Again, this is very vague, not very well constrained, because we don't know so much about the properties of the planets. A good thing about the model is that I can use it to tell which of the observationally unconstrained planet properties have the strongest impact on the surface climate. And that's very important, because if we want to maximize our knowledge on the occurrence rate and narrow it down as much as possible, then we need to observationally constrain these planet properties. And so what I found is that the surface pressure and the atmospheric composition have the strongest impact on the surface climate. And this is what we really need to study better observationally. Okay, so the code is on GitHub. You can download it and plug in your own PDFs or your own observational data. Just play around with it. It's called Hunter, the Habitable Zone Uncertainty Estimator. And with that, I thank you for your attention.
Plenty of time for questions. Francis.
Yeah, so interesting. So, I mean, doing something like this, I guess, is pretty, some of the assumptions are pretty centered, right? So, like, 1AU, I think like we have a high probability of finding or habitable planet. Right? That's rooted just because we're assuming that Earth is supposed to.
No. So, okay. Yeah. So, for the observational unconstrained variables, this is the list of different PDFs I used. So, let's see. For the planet mass, I assume that they can be like the rocky planets in our solar system, so mostly silicate and irons. But I also have a PDF which is more similar to the moons of Saturn and Jupiter, so they are mostly water, maybe a small amount of silicate, so that is very different from Earth. For the atmosphere type, I have Earth-like atmosphere compositions, right, nitrogen, CO2, but I also have hydrogen compositions in there, so again, that's not Earth-like. The surface pressure, I have log distributions in there, uniform distributions in there, uniform in log space. These are all non-Earth-like, right? And the same goes for the surface albedo and the other parameters as well. So Earth is in there, yes, but everything else I could think of is also in there, which is not Earth.
The top probability here is 40%, so I guess the 60% others, what are they? Because they're interesting, right?
Yeah. Okay, so 40% was the average, right? What are they? Okay, so if you have a planet like Venus, okay, so let's assume you put Venus where Earth is today. It would, the surface of Venus then would still be too high to have liquid water on the surface. So that 60% or 30% or however you want to define it, those are planets that have a thick atmosphere with lots of greenhouse gases. So the greenhouse effect is strong, and therefore they are too hot to have liquid water on the surface. The other extreme is planets that have a thin atmosphere with very little greenhouse gases. And if you put such a planet at the orbit of Earth, the surface temperature would be too low for them to have liquid water. So you have both extremes in there. It really strongly depends on the atmosphere properties of the planet, whether you have water on the surface or not.
How did you account for the albedo of the planet, or how was that?
The albedo, okay, so for M dwarfs, I don't know if you know about the ice albedo effect. So what happens is that the albedo of ice is roughly 1 if you have a solar type star, because solar type stars radiate in the optical wavelengths. If you go to M dwarfs that radiate mostly in the near infrared, then the albedo of ice is only 0.4. So when I calculated this figure, the range of surface albedo was between 0 and 0.4, and I had all kinds of distributions in between linear, log, whatever you can think of.
Anything else? Yeah, hold on, one.
Well, the value again in this 0.4 depends on the ratio of probability of how big your posterior PDF are, right? So as we discover planets, can you adapt each of them to say, okay, like a thick atmosphere, say at a certain insolation is very rare?
That's exactly that.
At the moment, they're all equal, you say?
Sorry?
At the moment, all of them are treated equally, and then as our knowledge increases, we can.
Exactly, yeah. So if you observe the atmospheric composition of an exoplanet, and you tell me what is the distribution of values for the composition, I can plug that in and see, how this probability kind of shrinks and converges towards the value. And the trick is that, if you know the atmospheric composition, you still don't know the surface pressure. So you don't know whether you see the top of a cloud deck or the surface. So the probability will, the range of probability will become smaller, but with the atmospheric composition alone, you will still not get the final answer yes or no. You just shrink the range.
All right, let's thank Andras again. Before people go out for coffee, we have an announcement about posters.
All right, can I have your attention before we go to coffee break? We have two important announcements. The first one, or the second one,